A fan coil unit is a device that uses a coil and a fan to heat or cool a zone. Indoor air moves through the coil, either being heated or cooled, and then back to the room. Fan coil units are essentially small-scale air handling units installed throughout the building. They receive chilled water or hot water or both from a chiller and a boiler without extensive ductworks. They're available in ceiling, floor-mounted, freestanding configurations. Fan coil units are typically less expensive to install than duct systems. This diagram shows a two-pipe ceiling mount fan coil unit system in which a fan drives the indoor air through the coil and back to the space. Each of the units only has one supply pipe and one return pipe. The pipes are connected to the chiller and the boiler. However, they run either hot water or chilled water, not both. It means the system either provides heating or provides cooling, so there is a lack of flexibility. All building areas must operate in the same mode. Heating some areas while cooling others is not possible with this design. Four-pipe fan coil units have two sets of coils and two sets of piping connecting to the chiller and the boiler. These systems can deliver cooling and heating simultaneously by using the chill water and hot water coils at the same time, so that the building can be cooled or heated simultaneously. With more piping, four-pipe systems are more expensive to install and requires more space to accommodate the additional pipes. The increased number of connecting points and valves also results in more maintenance. Fan coil units, especially the four-pipe version, can be a good candidate for facilities with a relatively low occupant density, such as housing, residential complexes, hotels, dormitories, military facilities, etc. In either a two-pipe or a four-pipe system, dedicated fresh air intake with exhaust heat recovery should be provided to emit outdoor fresh air and maintain indoor air quality. The outdoor air can be either integrated in series with the fan coil unit, such as the example shown in this diagram, or decoupled by using a separate set of small ducts in parallel with the unit. An energy recovery unit, ERV, in this design allows fresh air into the building while retaining preconditioned heating or cooling by a heat exchanger. A small amount of stale air is drawn back to the ERV through a set of small ducts and pushed to outside as exhaust. An active chill beam is essentially a fan coil unit without the fan. An air ventilator sends the primary conditioned fresh air to each chill beam unit, either suspended from or recessed in the ceiling. The primary air passes through nozzles, which induce air from the space up through the cooling tubes that connect to the chill water piping. Unlike fan coil units, chill beams do not contain a condensation drainage system. Therefore, the primary air must be dehumidified to the level that will not cause condensation in the units. This diagram shows a two-pipe active chill beam system in which an energy recovery ventilator emits fresh air from the outside, dehumidifies it, and sends it to all chill beams through small air ducts at the primary air, which induces the existing indoor air to pass through the chilled water tubes within the chill beams. A water-cooled chiller supplies chilled water to each beam. Chilled beams are quiet because there is no fan in the unit. Air duct size is much smaller than the conventional all-air systems because it only needs to move the amount of air required for maintaining indoor air quality. The smaller duct can reduce the interstitial space height to save cost and/or increase seating height. As cooling is primarily delivered by water piping throughout the building, it reduces the fan power to move air and the energy loss through ductworks. Disadvantages are high initial costs and a high level of humidity control of the incoming air. Passive chill beams do not have an air connection. Instead, they rely on buoyancy of air. The unit is suspended from the ceiling and has a fin and tube heat exchanger cooled by chilled water running through the tubes. Warm air from the space rises up, and the air surrounding the heat exchanger is cooled and descends, creating a convection. The passive chill beam by itself is an all-water passive system without using a fan. Therefore, it typically has lower energy consumption and operation costs than the conventional all-air systems. This diagram shows a passive chill beam system in which a water-cooled chiller supplies chill water to the beams. Passive chill beams require fresh air to be delivered by a separate air handling system, for example, by an energy recovery ventilator similar to active chill beams. Fresh air needs to be preconditioned, dehumidified to prevent condensation forming on the heat exchanger. A variable refrigerant flow system delivers refrigerant, not chill water, to the zones. Based on the indoor requirements and outdoor conditions, the refrigerant's flow can vary from zone to zone, delivering just the appropriate amount of refrigerant that each zone needs. A single outdoor condenser can serve many independent indoor units. Variable refrigerant flow systems provide space cooling and heating by circulating air within the space. To maintain indoor air quality, fresh air from outside needs to be provided separately, for example, by an energy recovery ventilator. This diagram shows a variable refrigerant flow system in which one outdoor condensing unit serves a number of indoor terminal units. Each indoor unit serves a thermal zone controlled by a controller, often remotely, to set temperature, fan speed, etc. This system is similar to mini-split, but in a larger capacity. An energy recovery ventilator provides preconditioned and dehumidified fresh air to the zones to maintain indoor air quality. Next, we will introduce two auxiliary HVAC components, Economizer and energy recovery ventilator. Both involve the incoming fresh air and outgoing exhaust air in a typical air handling unit. An economizer is a mechanical component that draws in outside air and uses the outside air only for cooling a building when the air temperature is cool and dry enough, and this is called free cooling. The entire or a substantial part of the return air from the space is released to the outside. Economizers reduce energy costs by using outdoor air for free cooling, and it causes the compressor to run less. When free cooling is not available, outside air and exhaust dampers switch to minimum to maintain indoor air quality. When free cooling is available, outside air and exhaust dampers switch to maximum to use only outside air to cool the space. All retained air is released to outside in that case. These dampers are closed to prevent retained air from recirculating back to the space. An energy recovery ventilator supplies air to the building and exhausts stale air. ERVs reduce energy consumption and improve air quality, especially for residential buildings designed to rely on infiltration for fresh air intake, but are built with increasingly airtight methods. Geothermal heat pumps use the stable temperature of the earth to either cool or heat the outside coil of the heat pumps. Underground temperature ranges from 45 degree to 75 degree F. It is warmer than the outside air during the winter and cooler in the summer. Geothermal heat pumps circulate an antifreeze solution through a closed loop buried in the ground or submerged in water. The heat between the refrigerant in the heat pump and the antifreeze solution is transferred by a heat exchanger. The loop can be in a horizontal, vertical, or pond lake configuration. This diagram shows a horizontal ground loop, where the heat exchanger transfers heat between the refrigerant in the outdoor coil and the solution in the ground loop. Horizontal ground loop is the most cost-effective configuration, especially for building sites where sufficient land is available. Horizontal loops require a substantial amount of open ground space for installing the pipes. It requires trenches at least 4 feet deep to bury the horizontal piping, which is often coiled and stacked to provide more area for heat transfer. Vertical ground loops are installed in holes approximately 4-inch in diameter, drilled deep into the ground, usually to a depth of 100 to 400 feet, or even more. The loop pipes are placed into these holes, which are typically placed about 20 feet apart. Vertical ground loops are appropriate for sites where there is little ground area available for the loop installation. Water loop may be the configuration with the lowest cost if there is a water body near the site, such as a pond. Supply pipes with working solution are installed underground from the building to the water and shaped into coils. They are placed at least 8 feet under the surface to prevent freezing. In the winter, the interior surfaces of the building perimeter walls and windows are often at low temperatures, especially the windows with low R values. These cold surfaces become cold sinks, and an occupant in close proximity becomes a radiator. The occupant's body begins to radiate his or her body heat to the cold surface nearby. The closer to the perimeter, the greater the discomfort. In this case, the occupant feels cold due to the low radiant temperature in the space, even though the air temperature in the room is still at a comfort level. Perimeter heating, such as fin tube or radiant panel, can be added at the perimeter zones of the building, usually below the windows, as a supplementary heat source to elevate the radiant temperature. A fin tube is made of aluminum fins that are pressed onto a copper pipe. Hot water flows through the pipe and heats the fins. The space in between the fins allows the air in that space to be heated. As warm air rises, it exits the housing, heats the window above to raise its surface temperature, and eventually heats up the space by convection. Fin tubes involve extra maintenance due to the large amount of piping joints and valves. They may also be in the way of system furniture in offices. Radiant panel is another option for offsetting the heat loss to the cold surfaces of walls and windows on the perimeter of a building. A radiant panel not only uses air as a medium for heat transfer via convection, but also uses thermal radiation. Both fin tubes and radiant panels help control condensation, typically found on large exterior glass walls. The coefficient of performance, COP, is a metric commonly used to measure heat pump efficiency. The COP is the ratio of the heat output of a heat pump to its electrical energy input. Higher COPs equate to lower operating costs. Air source heat pumps generally have COPs ranging from 2 to 4, meaning that they deliver 2 to 4 times the energy they consume. Water source and ground source heat pumps normally have COPs ranging from 3 to 5. The COP of an air source heat pump decreases as the outdoor temperature drops. Therefore, 2 COP ratings are usually given for a system, one at 47 degree F and one at 17 degree F. The energy efficiency ratio, EER, of an HVAC cooling device is a ratio of the output cooling energy in BTU per hour to the input electrical energy in watts. At a given operating point, EER is normally calculated at an outside temperature of 95 degree F and an inside temperature of 80 degree F and 50% relative humidity. EER is an easy and accurate way to gauge how an AC unit will operate during the peak cooling time at 95°F outside. EER does not consider seasonal temperature changes, which makes it a standardized measure to compare the cooling efficiency of different AC units. The SEER rating of a unit is the cooling output during a typical cooling season divided by the total electric energy input during the same period. The higher the unit's SEER rating, the more energy efficient it is. In the US, SEER is the ratio of the cooling output in BTU to the energy consumed in watt-hours over a cooling season. An air conditioner with a higher SEER rating uses less energy to maintain a comfortable temperature, so it will cost less to operate than a system with a low SEER rating. Modern air conditioners have a SEER value ranging from 13 to 14 SEER as a minimum to a maximum of 21 or 25 SEER. Energy use intensity EUI is a building's energy use as a function of its size, which is expressed as energy per square foot per year. It is calculated by dividing the total energy consumed by the building in 1 year, measured in kBTU, by the total gross floor area of the building in square feet. Building EUIs provide important energy performance metrics for energy modeling and assessment of building energy performance. Building type is one of the main factors that determine EUI. Hospitals have EUIs that can range from 400 to 500 kBTUs per square feet. A school may have an EUI in the range of 150 kBTU per square feet. Climate can have a significant impact on EUI as well, due to the variations in heating and cooling ambient conditions.